Hello there. Heating our homes contributes a very significant proportion of our emissions in the United Kingdom. It's about 14% or a seventh. As a result, this is a worthwhile target on the trail to carbon net zero. And we can reduce emissions associated with the heating of our home and our hot water in several ways. By heating less, by insulating better, and by making the energy source one that has zero emissions. For the majority of pre-existing buildings, changing the energy source will have to be a component. In the UK, about 87% of home heating comes from natural gas and a further 4% from heating oil. And that has a higher carbon footprint compared to gas for the unit of energy. Only about 7% comes from electricity, and that's mostly from portable or storage heaters. And our own house here was predominantly heated by an oil burner with an additional option of an open fire for coal or wood. In 2010 we replaced the oil burner by a heat pump as a greening experiment, and we've learned quite a bit through this idealistic leap. But at least it meant we could have the oil tank removed from the front garden, and that's visible evidence from the fact that we are no longer burning lots of 2,500 litres, which would cause emission of 7 tonnes of CO2. Well, that early model lasted 11 years, but suffered a major failure this summer gone. And we decided it would be best if we replaced it with a new one, installed by a well-established local firm that we could envisage in our old age being around for a while and being a reliable provider for servicing. And that was an attempt at future-proofing. Ours is an air source heat pump. This is the previous one, and here is the new installation. In 2010, we had to install a large hot water storage tank, and all of that could be reused in this new installation. The tank is in the corner of the garage now, and for us that was helpful because it took the outer hot water tank in a cupboard upstairs, giving us some more storage space. But this does not work for everybody's home, and alternatives include air-to-air heat pumps, essentially reverse air conditioning. The new unit is much quieter than its predecessor. You have to be up close to it to know that it is on. A heat pump does not generate energy, rather the pump unit is a large version of a refrigerator working in reverse to squeeze the heat from the atmosphere. As a result, it pushes out a lot of cooled air, and for us, that goes out harmlessly behind the garage. An analogy is a pump for a tyre here on my electric bike. I'm not creating air, just collecting it into the tyre, and that takes a bit of energy to do. The operation of a heat pump also takes some energy. And so a key question is, how much energy do you squeeze into your house compared to the energy which is required to do the squeezing? The ratio between the energy you use and what you get into the house is called the coefficient of performance, or SCOP. It will vary with the outside air temperature and the temperature of the heated water that you are trying to deliver. The bigger the jump, the more energy is needed to achieve it. One advantage of a ground source heat pump is that you are taking heat from a near constant temperature source under the ground, but the installation requires either a significant area to lay pipes under the surface of the soil, or you need to drill down a borehole for the pipes to go into. And not everyone can or would want to take up this option, but generally it affords a higher and pretty constant COP value. Experimentally, we're trying to measure the seasonal coefficient of performance, the SCOP, also called the seasonal performance factor, or SPF. Our installation was in mid-August and it is now mid-December. Over that 4-month period, the average value is 3.7, but that was 4.7 during one particular month. So taking the average for every 100 kilowatt hours of the pump is used, the house has received 370, and the pump has provided us the extra 270 kilowatt hours. So what effect does that have on our energy use? This graph shows the energy use per day for each month in 2021 in the dark curve. As expected, it was highest in January and was lowest in midsummer. The yellow curve is the electrical energy that might have been generated by a 4 kilowatt peak power solar array panel if we had one. This data comes from that recorded on a very similar array on a south-facing roof of a church hall just 2 miles away. It shows that in the period of spring to early autumn, a very significant of the energy we used could have been generated by the PV array, but would need a well-matched battery to use it all, and by that I mean that the capacity closely matches the daily generation. Most of the energy we expend is in the colder months, and we're just beginning to put together the data from the helpful app that comes with a new pump. The heat pump performance is detailed in this figure. Over the summer, the heat pump will scale with the hot water use, and in the winter with the space heating in the house. In the winter months, it is looking as though the energy squeezed into the house by the heat pump is about the same as the electricity used to drive the pump and also everything else in the house. So in effect, the heat pump has halved our electricity consumption in November and December. Overall, this is much more energy over the year than the solar panels would generate. The heat pumps have allowed us to eliminate the use of heating oil, saving its combustion to CO2. They have considerably also reduced our electricity use, or a substitute for the energy source of the heating oil. Since we take electricity from a green supplier, we might claim to approximate to carbon zero for this aspect of our emissions. But really we aim to reduce our electricity use more. We have already improved insulation by doors and windows, have LED lighting and switched outdoor lights mostly to solar-powered ones. Now it's the mundane but very important stuff to make the heating more efficient. We've fixed the radiator's thermostatic valves upstairs, and problems with the valve controllers downstairs hopefully will be fixed next week. Then we can tweak the settings on the heating to use less green energy. But in terms of running costs, well, at this time, the cost of natural gas per kilowatt hour was 5 times less than that of grid electricity. That makes little sense if the aim is for the country to reach a zero carbon target. At present, the cost ratio fights against carbon reduction. That may change. It's influenced by fiscal measures. Also, the costs of renewable sources like wind and solar have dropped in relation to fossil fuels, and they're still coming down. It may be that in a year or two the COP gain of 3.7 in our reading over the last 4 months will cross over the price ratios to make this greener option for home energy more attractive, and that is our hope.